Hi, I am Samik Dutt and I will be solving question number 2 of homework 10. So, in question 2, first we will begin with a wide sense stationary process, which is WSS. A stochastic process XT is called wide sense stationary if its mean is constant and its autocorrelation depends only on tau equals T1 minus T2. That is, expectation of xt equals to eta, which is constant, expectation xt plus tau xt are tau. Since tau is the distance from t to t plus tau, the function r tau can be written as symmetrically as xt plus tau by 2 x star t minus tau by 2. Also, expectation of modulus of x t square equals to r naught r0. Thus, the average power of a stationary process independent of Tn is equals to r0. That Poisson increment process, Poisson impulse process, random telegraph signal are all WSS process. So now, next is the independent increment process. So xt is a process with independent increments if probability xta minus xtb less than equals to x1, xtc minus xtd less than equals to x2 can be written as xta minus xtb less than equals to t1 times xtc minus xtd less than equals to x2 for any non-overlapping intervals. So examples include Poisson process, random process, Wiener process. So we can, since these increments are independent of each other, the process has no memory of its past behavior and its future behavior is completely independent of its past behavior. Now we go to the third, which is the Markov process. The Markov process X is xt if the past has no influence on the statistics of the future under the condition that the present is known. That is, for any n and t1 greater than t2 greater than up to tn, we have probability of x t1 is less than equals x1 given x t2 equals x2 x t3 x3 up to xtn equals xn is equals to probability of x t1 less than equals to x1 given xt2 equals x2. So Markov process is memoryless and its future behavior does not depend on its past behavior and only depend on its current behavior. So the examples include Poisson process, semi-random, telegraph signal, random walk, etc. So now the fourth part, normal process. Stochastic process xt is said to be normal if the random variables xt1, xt2 up to xtn are jointly normal for any n, any t1 up to tn. That is fx, x1 up to xn, t1, t2, tn can be written as 1 over under root 2 pi n root epsilon e to the power minus half x minus eta to the power transpose C inverse x minus eta, where eta equals to expectation x, C is minus x minus eta transpose. C is the autocovariance matrix, which is symmetric and positive definite. So to definite. Now, fifth, strict sense stationary process. A real stochastic process is stationary in strict sense if a statistic is not affected by a shift on the time axis. This means that two processes xt and xt plus epsilon have the same statistic for any epsilon. Xt is strict if and only if fx x1 to xn t1 to tn equals to fx x1 to xn t1 plus epsilon t2 plus epsilon so on, any n, any t1 to tn and any epsilon. Okay, now next is the white noise. White noise is type of stochastic process that has constant power spectral density and is uncorrelated at different points in time. A process Vt is a white noise if its value Vti and Vtj are uncorrelated for every Ti and Tj is not equals to Ti. So covariance Tj is equals to 0, Ti is not equals to Tj. A non-trivial white process must be of the form if a covariance is Qt1 delta T1 minus T2, Qt is greater than equal to 0, called where Qt1 is called the average intensity. Now we come to mean ergodic process. Stochastic process xt is called ergodic if all of its can be from a single sample. Xt is mean ergodic if limit t up to infinity 1 by 2t minus t to t. Xt dt is expectation of xt in mean square sense. Also, expectation of xt equals to eta, which is constant. Mean square sense means that limit t approaching infinity x by 1 over 2, expectation of 1 over 2t minus t to t x t dt minus eta square equals to 0. Intuitively, mean ergodicity implies that behavior of the process over time is representative of its average behavior across all possible realization. This property is important because it allows us to make predictions about the future behavior of the process based on its average behavior. It reduces the number of parameters that need to be considered for analysis purposes. So now the eighth part, sorry. Martingales. Martingale is a sequence of random variables whose expected values does not change over time. Discrete time martingale can be defined as discrete time stochastic of x1, x2 up infinity, xn that satisfy for any time n. Expectation of modulus of xn is less than equals to infinity, and expectation of xn plus 1 given x1 up to xn equals to xn. That is the conditional expected value of the next observation given all these is equal to the most recent observation.